In this lecture, we're going to take a look now at all the mechanisms that go in together to produce urine. So we're finally going to put it all together and make sense of how urine gets produced. So if what we've got here in this illustration is the glomerulus, the proximal convoluted tubule, and the nephron loop, we're going to we now want to think about what's happening to urine as it passes through the nephron loop. So here at the far end of the nephron loop, we've said, let's maybe start here in two places. As the fluid enters the nephron loop, it's isotonic to the fluid around it. So here at this point and at this point, they are equal in concentration. But at the far end of the nephron loop, because of the activity of the nephron loop, the fluid is now hypotonic. So it is more concentrated outside. So it's not equal, but it's concentrated outside compared to the inside. And the book introduces here a concept called osmolarity. So if the osmolarity is how much, what the osmotic pressure, you can think of it as a way of quantifying the osmotic pressure that the fluid has. And so when we start, it's about 300, when it starts to go into the nephron loop, milliosmoles. That's the osmoles, or the, oops, sorry about that, they're the unit. And here at the far end, it's going to be about 200 milliosmoles. So this osmolarity increase, or decrease I should say, is the result of the distal convoluted tubule being mostly impermeable to water. Okay, so here at the distal convoluted tubule and at the rising, at the ascending portion of the limb, it's impermeable to water, so it doesn't have the chance to become isotonic, let's say. All right, so this is the setup as we go into the proximal, or into the descending limb, about 300 milliosmoles, and it's isotonic to the fluid around it. So that means it's about 300 milliosmoles outside of the nephron loop, so that by the time we get to the end, the fluid is 200 milliosmoles and it's about 300 milliosmoles outside of the ascending limb. Alright, so this dilute fluid, this more dilute fluid here at the ascending limb, at the end of the ascending limb, is the result of countercurrent exchange, which is a function of this exchange of material caused by the countercurrent multiplier effect of the nephron loop. Countercurrent exchange is, so the countercurrent piece is that the fluid is flowing downward in the descending limb, and then right next door it flows in the opposite direction. So that's what we mean by countercurrent exchange. And in class, I used the example of a penguin standing on an iceberg here. So if we have the penguin standing on the iceberg, this is supposed to be the penguin's feet. In the penguin's legs, we see countercurrent exchange in order to prevent the penguin from losing all of its heat out here out of its feet. And so what happens is that as the, each time I touch it, I'm sorry, As the blood flows back upward from the feet, it's carrying cold blood. But as the cold blood goes upward, it robs heat from the opposite side, from blood that is flowing downward, so that by the time the blood, that cold blood, gets up the leg, it's taken heat. It's removed all the heat that was available in the blood going down the leg. So here we have cold blood. Here it's warm by the time we get up to the top. And as the blood is flowing downward, the heat flows, because heat moves just like from high warmth to low warmth. This warming blood moves heat over, so that always the blood going down the leg is going to be about the same temperature as the blood going up the leg, but because it's slightly warmer here, the heat can flow in a downhill direction from warm to cold. So it's the same thing that's going on here that causes countercurrent multiplication. We see on this side, on the descending limb, which is very permeable to water, we're going to see water movement, but it's easiest to explain it by what's going on here at the ascending limb first. So there's an osmotic gradient that is set up here as we make our way down the tube. And this osmotic gradient goes from 300 milliosmoles, I should put this here, 300 milliosmoles where it's isotonic, down to about 1200 milliosmoles. And because the descending limb is permeable to water, that draws water out of the descending limb, so that as we're working our way down the descending limb, the fluid inside of the descending limb is always going to be isotonic to the fluid outside. So we go from 300 to 400 to 500 to 600, all the way down to 1100 and then 1200. And because the fluid is slightly, inside the limb, the descending limb, because the fluid is slightly less concentrated, water is always going to be flowing outward all the way down. So in the descending limb, the fluid is constantly remaining isotonic to the surrounding tissue fluid inside the kidney. But because the tissue fluid is becoming more and more concentrated in salts, we drag more and more water out of the fluid until by the time we get down to the bottom of the descending limb, the tubular fluid is about 4 times as concentrated as it was at the very beginning of the descending limb. So we go from 300 to 1200 milliosmoles. Now, on the ascending limb side, the fluid is trapped in the ascending limb because this thick limb is impermeable to water. So when the fluid now turns to go back upward toward the cortex of the kidney, then we see active transport that removes sodium from this really concentrated fluid. So remember, it was 1200 milliosmoles, super concentrated, 4 times as concentrated as it was when it entered the descending limb. Now we can move material along the concentration gradient out of the developing urine on the ascending limb side. And this is what sets up our concentration gradient outside, because as we make it through the ascending limb, we're removing sodium, removing sodium, removing sodium, It's easier to remove sodium at the beginning because it's so concentrated. And so that creates this osmotic gradient that the descending limb is responding to as the fluid, as we pull out salt, pull out more salt, pull out more salt, until we get to the very top where it's about 200 milliosmoles inside, and outside of the descending limb it's 300 milliosmoles. And here is where we have hypotonic fluid. It becomes hypotonic because we've pulled out so much sodium, and when we pull out all that sodium, the chloride just follows along. So we pull out, we remove positive sodium ions, and that just drags along with it negative chloride ions. So by the time that we get to the top of the ascending limb, that really concentrated fluid is now very dilute, and it's also low volume. So the function then of the nephron loop is to first pull out water because of the osmotic gradient that we're seeing on the descending limb of our countercurrent multiplier here, and that makes the fluid very concentrated. And then on the ascending limb side, we pull out sodium and chloride ions, which makes our concentrated fluid now, that's become very low volume and concentrated, it makes our concentrated fluid very hypotonic, so that the fluid volume doesn't change, but the tonicity of the fluid changes. And we pull out all those sodium ions, making what was really concentrated fluid and concentrated low volume fluid into a low volume but hypotonic fluid. Alright, so hopefully that makes sense now. The action of the fluid going through the nephron loop is going to create hypotonic fluid by the time we get to the very end, and it'll be much lower volume. So we've seen now the countercurrent multiplier effect that causes increasing sodium concentration both outside and inside the nephron loop. Now we also see this, the vasa recta. Remember the fluid that the blood that's in the peritubular capillaries that go across our nephron loop. So for some reason they show these rather than placing them right on top of each other, which is kind of what it would be like. They have them kind of offset a little bit. But here we see this countercurrent exchange happening that maintains the sodium in the kidney rather than allowing all the sodium to be lost from the kidney in the blood. So as we move, as the blood is flowing now along with our descending limb, and we're seeing the concentration of the kidney fluid becoming more and more concentrated, more and more salty, sodium will move into the blood, and we would lose it all if that sodium kept flowing away. But because of the blood flow that, because the blood's flowing downward, and then as it flows back upward, now remember the blood is going to be flowing with, against the let's see if I can say this right now. So because the blood is flowing countercurrent, that sodium that we put into the blood on the descending side of the vasa recta is now going to be, as it flows back, as the blood flows back upward, that sodium, just like we saw with heat, is going to be maintained in the fluids of the kidney, because the sodium then flows back out again taking the chloride ion with it. So we see countercurrent exchange happening that keeps the sodium trapped in the kidneys rather than being carried away by the blood. So by the time the blood makes it back up out of the center of the kidneys as well, as it moves back up again, we see that the sodium has been concentrated back again in the downward flowing of blood. And so this creates this loop of sodium flow and associated chloride flow that maintains the concentration gradients in the kidney of the salt. Okay, so we've seen how there is countercurrent multiplication as well as countercurrent exchange so that we maintain a concentration gradient in the kidney. And remember how we said that the juxtamedullary nephrons that have the very long loops, because they go deeper into the kidney, they're going to see even more of the water pulled out and then have even greater concentration changes as we pull the sodium out, and they are the ones that do a lot of that water reclamation that help to ensure that we don't leave a lot of water in our urine. So it's the longer loops that go deeper into the kidney that experience the greatest osmolarity change, that do most of the water reclamation, or a lot of the bulk of water reclamation. All right, so now how do we regulate the concentration of urine, the concentration of the urine and the volume then of the urine? Well, there's antidiuretic hormone, and remember, diuresis, that means the production of large amounts of diuresis. There we are. That's the production of large amounts of urine. So antidiuretic or antidiuresis then would be the production of lots or very little urine. So antidiuretic hormone is produced when we have low water concentration in the blood and tissue fluids. And what it does is it conserves water and prevents us from losing water from the body in the form of urine. So now we're looking at the distal convoluted tubules and the collecting ducts. Generally, the distal convoluted tubule and the collecting ducts are going to be impermeable to water. So without any antidiuretic hormone, then they're going to be impermeable to water. And as the collecting duct makes its way once again back through the very concentrated, remember we've got this concentration gradient where we go down here at the bottom, it's about 1200 milliosmoles. Well, now the urine, as it makes its way toward the renal pelvis, is going to have to go through the collecting ducts, which are passing through this concentration gradient. So without any antidiuretic hormone, because the distal convoluted tubule and the collecting ducts are impermeable to water, we're going to lose all the water, that we're going to lose a hypotonic urine, because remember, at this point it's hypotonic to the fluids around it. But with antidiuretic hormone in circulation, thanks to release from the posterior pituitary, then we're going to open up little channels here that will allow us to reclaim water as the fluid flows through the distal convoluted tubule and the collecting duct. And so with antidiuretic hormone, we're going to see water coming out of the developing urine, making the developing urine more and more concentrated as it passes through the collecting duct. And so as a result, we produce a low volume urine that's highly concentrated. Alright, so what are some of the materials that we find in highly concentrated urine? Well, urea and uric acid, we've said, are two of the nitrogenous wastes that we find in urine. Urea is produced as we metabolize amino acids. So when we use amino acids for energy, or we strip off the nitrogen the amino group from the amino acid. And so the more proteins we eat, then the higher the concentration of urea that we find in the urine. And, oops, there we are, sorry. And because we can pull it at the proximal convoluted tubule here, and because we remove urea from the developing urine, which I know doesn't make sense yet, we'll make sense of that in a minute, it's one piece of what creates this osmotic gradient. So urine adds to the osmotic gradient that causes us to reabsorb water as we go down the descending limb. So uric acid is the product of nucleic acid metabolism. So as we break down two nucleotides, adenine and guanine, these two nucleotides, as we break them down, we produce uric acid along the way. It is actively transported from the tubular fluid, and we remove we completely reabsorb uric acid, but we then later on resecrete it so that about 10% of the uric acid that has been reabsorbed from the developing urine gets returned to the urine. By the time we make it through all of the nephron, we pee away about 10% of the uric acid that we filter out of the urine. So it's kind of an odd thing with uric acid. We reclaim it all, and then we put about 10% of it back into the developing urine. So what is urine then? Well, it's mostly water, about 95% water. Then there's the urea and the uric acid that we put into the developing urine, which is a nitrogenous waste. There's creatinine, which is also it is a breakdown product of creatine. Remember, creatine phosphate that we use in muscle function. So we lose some of that creatine and we convert it into creatinine and then pee it away. And it has trace amounts of amino acids, so there'll be a little bit of amino acid that escapes, and electrolytes, things like sodium and chloride and potassium. But we reclaim most of the sodium that we lose in urine, but we do get rid of lots of electrolytes, especially potassium. So that by the time we are done with all of this concentrating of the urine, reclamation of the water that's in it, we produce between 0.5 to 2.5 liters of urine a day. So, imagine like a 2-liter bottle of urine being produced every day. So, producing between 50 and 60 milliliters of urine an hour is fairly normal. Producing less than 30 milliliters an hour can be indicative of kidney failure, so there's something going wrong when we produce very, very low volumes of urine. So here we are looking at a summary now of all of the factors that go into urine production. So at the glomerulus, we filter out plasma from the blood, removing something on the order of 20% of the plasma that's in the blood. Then at the proximal convoluted tubule, we do lots of reabsorption. So by active transport, we pull back glucose, any amino acids that have escaped, creatine, that should have an E at the end of it there. So creatine and the metabolic acids, remember citric acid and lactic acid, so on. And then lots of the ions that we have put out into the urine. So phosphate ion, the bicarbonate ion, calcium, potassium, and sodium ion. So all of this stuff is returned to the body by active transport. If there are any proteins, we do endocytosis to reclaim any proteins that have gotten into the developing urine. And we remove by osmosis lots of water. And then because chloride ion gets kind of entrained when we pull sodium back into the blood, then chloride just kind of follows along. And so it is electrochemical attraction that moves sodium back into the body. So lots of reabsorption at the proximal convoluted tubule, and some tubular secretion occurs there. So we will put histamine, pharmaceutical drugs, creatinine, so we pull back in creatine, but we will tubular secrete creatinine, and we also will secrete hydrogen ions. So all of this secretion happens by active transport. It takes ATP to move it. So in the descending limb of the nephron loop, we reabsorb water. That's primarily by osmosis. At the ascending limb, we reabsorb sodium and potassium by active transport, and chloride ion kind of gets entrained because of electrochemical attractions. At the distal convoluted tubule, we reabsorb more sodium by active transport. So we're able to make the fluids there at the distal convoluted tubule even more hypotonic. And we can secrete hydrogen and potassium ions by active transport. So we can put those back into the blood. And then remember that if ADH is provided in the blood from the pituitary gland, then we add those aquaporins in, and we can do osmosis to reclaim even more water from the developing urine. Okay, so we can use the ability of the urine to reclaim or to secrete, so to reabsorb or to secrete materials to test kidney function. The inulin clearance test introduces inulin, this complex polysaccharide, into the blood. It is indigestible, and it is filtered out into developing urine, but it's not reabsorbed or secreted. And so we can use this as a way of determining how much glomerular filtration is being done at the glomerulus, because any of the inulin that arrives in the urine gets there through glomerular filtration, not through any tubular secretion. So inulin clearance looks at glomerular filtration rate. Creatinine clearance also tells us a little bit about glomerular filtration rate, because it's found at constant levels in the blood, and it's filtered out, but it's not reabsorbed or secreted. Then it can tell us a little bit as well about glomerular filtration rates. And then para-aminohippuric acid, or PAH, plasma clearance test, because it's secreted at the proximal convoluted tubule, so it's placed into the urine at the proximal convoluted tubule, it can be used to estimate total blood flow through the kidney if you know hematocrit. And so that gives us an idea of how much blood is flowing through the kidney. And you can read about these tests in the book a little bit more if you like. Okay, so there we have it. We produce concentrated urine when there is lots of antidiuretic hormone in the blood, and countercurrent exchange is what really causes the concentration of our urine that really rips away the water, pulls the water, reabsorbs it at the descending limb, and then we do active transport to get the sodium out to produce hypotonic urine at the end of the ascending limb. Alright, there you've got it. Hopefully that made some sense. If you have questions about countercurrent exchange and countercurrent multiplication, please don't hesitate to send me an email.